Hello, I am Seema and welcome to part 32 of the chapter Hydrocarbons. We were studying about alkenes. From this video onwards, let us start studying the next category of hydrocarbons, that is alkynes. In this video, we are going to study about the nomenclature of alkynes and isomerism in alkynes. But before we do that, let us understand what alkynes are. Alkynes, just like alkenes, are unsaturated hydrocarbons. Just to remind you of what saturation is, every carbon can form 4 bonds. We say carbon is tetravalent. Carbon has 4 electrons in its outermost shell. In order to complete its octet, it needs to form 4 covalent bonds. If carbon forms these 4 bonds with 4 separate atoms, it is saturated. But if carbon forms a double bond or a triple bond with any atom, thereby if carbon is forming 4 bonds, if even 2 of these are with the same atom, the compound is no longer saturated, it is unsaturated. Why do we say saturated or unsaturated? Carbon can form a maximum of 4 bonds. If it is forming, every carbon in the compound is forming 4 separate bonds, there is no chance of adding any more atom to that compound. Therefore, it is known as a saturated hydrocarbon. Assuming that it is only a hydrocarbon and there are no substitutions of oxygen or nitrogen or any other atom in the molecule, they are pure hydrocarbons. But if between 2 carbon atoms there is a double bond, as we studied in the previous topic that we did, alkenes, if there is a double bond, that is if there is a single pi bond in the compound, we call those compounds alkenes. Or if there is even one carbon-carbon double bond in a compound, we call it an alkene. Similarly, if there is even one single carbon-carbon triple bond, such compounds are known as alkynes. And therefore, since there are pi bonds in this, and since carbon is not forming 4 single bonds, every carbon, two of the carbons are sharing a triple bond between each other, they are unsaturated. So, alkynes are unsaturated hydrocarbons. They are identified by seeing the presence of a triple bond. HC I've just used for hydrocarbons. They are unsaturated hydrocarbons. They have a triple bond between 2 carbon atoms. They have a general formula. What is the general formula of alkanes, which are saturated hydrocarbons? The general formula for alkanes is CnH2n plus 2, if you remember. For alkenes, it is CnH2n, which means 2 hydrogens are less. Naturally, when there is a double bond between 2 carbon atoms, those 2 carbons would have had 2 hydrogens if they were all single bonds. But since 2 carbons are sharing a second bond, therefore those 2 hydrogens are lost, and the general formula of alkenes was CnH2n. But in alkynes, there is a triple bond between 2 carbon atoms. If it was a saturated hydrocarbon, imagine this one. These 2 carbons would have formed 3 bonds with 3 hydrogens, a single bond between 2 carbons, and 3 bonds with 3 hydrogens. So the formula would have been C2H6, that is CnH2n plus 2. It would have been an alkane, that is ethane. If you remove 2 hydrogens and form a double bond between these 2 carbon atoms, the general formula would be C2H4, that is CnH2n, which is the general formula of alkenes. But for alkyne, when you add one more bond and remove 2 more hydrogens, you get ethyne. And ethyne is CH triple bond CH. And therefore, it is known as ethyne, and it is unsaturated, and the general formula now will be CnH2n, which was alkenes had CnH2n. If you remove 2 more hydrogens and put another bond, it becomes a triple bond, and then the general formula becomes CnH2n minus 2, or the specific formula for this compound is C2H2. So C2H2 is Cn is 2, 2 2s are 4, 4 minus 2 is 2. Therefore, it is C2H2. Right? So the general formula of alkynes is CnH2n minus 2. Out of the alkynes, the first member, that is ethyne, is the most stable alkyne. In common nomenclature, ethyne is known as acetylene, And acetylene, since it is the most stable, it is the most commonly used compound among alkynes, therefore it is quite popular and it is known as acetylene. And in common nomenclature, all other members are written as derivatives of acetylene. I'll come to the nomenclature later, but then let us first talk about this compound acetylene. Acetylene in IUPAC nomenclature is known as ethyne. It is the most stable alkyne and it is quite inflammable. It burns very easily. Therefore, when you use oxygen, and since it is unsaturated, when it is unsaturated and with oxygen, it burns, it produces a very bright light, and the temperature at which it burns is pretty high. Therefore, it is used for welding purposes. It really increases the temperature. It is combustible, so you mix it with oxygen, and those welding torches that you have, that is an oxyacetylene torch, or that flame is known as the oxyacetylene flame. That is acetylene burning in oxygen. So you mix the two so that there is enough oxygen to cause the complete combustion of acetylene, to give that much of temperature, the temperature rises so much that the metal melts, and that causes the welding of the metal. So as I told you, let us now come to the nomenclature. In common nomenclature, all alkynes are named as derivatives of acetylene. For example, this is the first member, C2H2. If you talk of common names, CH, triple bond CH. In acetylene, the structure would be such that there would be one triple bond between two carbon atoms in an alkyne. So this is known as acetylene, and in IUPAC nomenclature, it is known as ethyne. We know for two carbon atoms, the word root would be ith, and since there's a triple bond between them, it is ethyne. Let us come to the next member, that is C3H4. C3H4 will have the structure CH3. Between two carbon atoms, there will be a triple bond, and the hydrogens would be 4. Or naturally, when you make a triple bond between two carbon atoms and count the number of hydrogens to fill up the structure, the tetravalency of every carbon, you will come to the same structure. Now, as I told you, in common nomenclature, this is known as the derivative of acetylene. So how do we identify what derivative? The two carbons which have a triple bond, that is known as acetylene. The two carbons having triple bond, if whatever other species is attached to the carbon is hydrogen, then we just write acetylene. But if it is an alkyl group, we name that alkyl group. Take a look here. The C, triple bond C. Here on this side there is only hydrogen, so this is just acetylene. But this carbon is attached to methyl. So in common nomenclature, we don't give the locants, and also we just commonly write that it is methyl acetylene. Come here now to this compound C4H6. Here CH3, CH2, C, triple bond CH. Okay, but first, before doing this, let us come to the IUPAC name. For IUPAC nomenclature, this has 3 carbon atoms. The word root will be prop. The ine is present on the first carbon, so we just write propyne or prop1 ine. For C4H6, we understand the IUPAC nomenclature should be butyne, but depending on where the triple bond is present would be the locant for the ine. So butyne would have 2 isomeric forms, or it can have 2 structures. So let us first make one structure, CH3, CH2, C, and there's a triple bond between these 2 carbon atoms. So according to the common nomenclature, C, triple bond C, and only H, this is acetylene. Okay, if in place of H there was any other substituent, we would have written that. But to this side of the carbon, or the acetylene part, we see there's a CH3, CH2, which is which alkyl group? It is the ethyl group. So this, in common nomenclature, this is known as ethyl acetylene, right? This part is acetylene and ethyl group is attached to it, therefore it is known as ethyl acetylene. But in IUPAC nomenclature, we'll count the total number of carbon atoms. There are 4 carbons, therefore it is but, and the ine is present on the first carbon, so we write it as but1 ine. Butyne can also be written in another structure, that is CH3, if the triple bond did not exist between the first and the second carbon, but existed between the second and the third carbon atom, then the structure would have been different. And what is that? That is isomerism. When molecules or compounds that have the same molecular formula but different structural formula, such compounds are known as isomers, or they are isomers of each other. They are related to each other because they have the same molecular formula, but they have a difference in their structural formulae. So this butane can be written as a different structure where the triple bond exists between the second and the third carbon atom, and here you will get CH3C, triple bond C, CH3. The formula is the same, 4 C's and 6 hydrogens, or C4H6. Now, according to common nomenclature, the 2 carbons with the triple bond, that forms the acetylene part. But you have a methyl group on this side and a methyl group on this side. So what do we write it as? We write it as dimethyl acetylene. The acetylene is here, and on both the carbons, methyl groups are attached, so it will be dimethyl acetylene. If it was pentene and there was one more CH3 here and a CH2 here, but a CH3 on one side, I would have called it an ethyl methyl acetylene. That would have been, you would have used it as ethyl methyl acetylene. But you know what happens with common nomenclature? As the structure becomes more and more complex, it becomes more and more confusing. And since there are no set rules in common nomenclature, one may tend to give different names to the same compound, and therefore it becomes difficult to identify compounds on the basis of common nomenclature. Only for a few compounds, the common nomenclature may be very common industrially, but IUPAC nomenclature is universally accepted. Therefore, for this compound, if you write down the IUPAC name, you would know exactly the structure of the molecule. So this has 4 carbon atoms, so we'll call it butane, but the ine is present on the second carbon. If I count from this side, 1, 2, the ine is between the second and the third carbon atom. If I count from this side also, it is between the second and the third carbon atom. So the name of this compound will be but2ine, right? So this was nomenclature. And while we did the nomenclature, I also gave you a little bit of hint of isomerism in alkynes. Now, isomerism in simple hydrocarbons can be of 2 kinds. Either they can be position isomers. I told you what isomers are. When compounds have the same molecular formula but their structures are different, we call them isomers. Isomers can be position isomers or they can be chain isomers. What does that mean? When the position of the triple bond, since we are talking of alkynes here and our focus is the triple bond, if the triple bond, the position of the triple bond is different, the isomers are known as position isomers. That was the case in but1ine and but2ine. The position of the triple bond was different. So such isomers are known as position isomers. And if the carbon chain itself is branched and has a different structure, those isomers are known as chain isomers, that the chain itself is different in their case. So there are 2 types of isomers possible, position isomers and chain isomers. So butane, we have already done the 2 types of isomers. What kind of isomers are these? These are position isomers. And the 2 isomers, the IUPAC names of the 2 isomers will be but1ine and but2ine. I have not written down the structures because they are written here. And you understand that. So let us come to the next member, that is C5 and H8, and see what isomers are there. Now the question is, you had propyne 2 and ethyne. Can they have isomers? They cannot, because you cannot, there are only 2 carbon atoms. You cannot change the chain, you cannot change the position. They are just, it is like a line can exist between 2 dots, and just that one line can exist between 2 dots. So 2 carbons have a triple bond between them. There are only 2 carbon atoms. Naturally, this is the only compound. There is no variation possible. In the case of propyne also, although there is a methyl group on this side, if I shift the triple bond on this side and bring the methyl group on this side, I will only change the sequence of counting. I will start counting from this side to write the name of the compound. It is as if I'm looking, if I have the triple bond here, I'm looking at the compound from this side. But if I have the triple bond here, I'm actually keeping it here. I'm looking at the compound from behind the board. So it will only appear to be on the other side while actually it is the same compound. So ethyne and propyne cannot have isomers. You need at least 4 carbon atoms to show some shift, a shift in the triple bond or a shift in the position. In the case of butane also, you can only show a shift in the position of the triple bond, not in the chain. Because even if I tried to make a branch, let us say I put this methyl group here. I cannot put the methyl group here because there is a triple bond and this carbon is already forming 4 bonds. It is not possible for it to form another bond. So if there was a branch, let us assume, if we call it a branch, I can only shift this carbon here and write the CH3 here, which would mean nothing. It only means that I have turned the bond. It does not mean that it is a new bond. The chain is still the same. So this does not show chain isomerism, it only shows position isomerism. But when you come to C5, that is pentyne, from pentyne onwards you can see a position isomer, in addition to position isomer, you can see chain isomerism too. So let us now see the different isomers of pentyne. The first one is the straight chain and the triple bond is between the first carbon and the second carbon. So that is the simplest structure. So CH, triple bond, C, CH2, CH2, CH3. So 1, 2, 3, 4, 5. What is the formula? There are 5 carbons. How many hydrogens? 3, 4, 5, 6, 7, 8. C5H8. All the isomers will have the same formula. Naturally, that is why you are only shifting the bonds and making the different isomers. So give the IUPAC name of this. This will be pent1-ine. If the position of the triple bond is shifted from the first carbon to between the second and the third carbon, then the formula would be this: CH3, C remains. These two are the ones which have triple bond, so CC triple bond, and CH2, CH3 remain as such. Now the structure has changed. Now this molecule will be known as pent2-ine. The triple bond has shifted from first and second carbon to second and third carbon. If I shift the triple bond between third and fourth carbon, would it form a new isomer? It would not. Again, why? Because I will now start counting from this direction, and if the triple bond was between these two carbons, I would get 1, 2. That is 2, pent2-ine. The name of the compound will still be pent2-ine. So it means it is the same compound, only we are looking at it from the other direction. So that would not be a new compound. What other variation is possible? In case of position isomers, you cannot change the triple bond. If I shifted the triple bond here, again I would count from this direction and it would be pent1-ine. So you will get just 2 position isomers, that is pent1-ine and pent2-ine. But you can get a chain isomer, you can make a branch here. If the triple bond is between the first and the second carbon atoms, then it is possible to make a branch on the next carbon. You cannot make a branch on this carbon because it already forms 4 bonds. This is the terminal carbon, the branch, it doesn't, you cannot have a branch on the top of the tree. That is only the tree growing taller. Or on the bottom, that is only the root growing taller. You can only have branches in the middle. So you can only have branches on atoms which are in the middle, not on the terminal carbons. And this carbon already is forming 4 bonds, so you cannot form a branch here. The only carbon available for forming a branch is this one. So you make a branch here, you get CH3, CH, CH3, C triple bond CH. Give it the IUPAC name, it still has the same formula, C5H8. But according to IUPAC nomenclature, now this is a branch and the parent hydrocarbon has only 4 carbon atoms. So this becomes butyne. And the methyl group is attached to the third carbon. So because the ine will get precedence, the methyl group is only a substituent. It is not a functional group. So when you are naming this compound, the ine will be more important than the methyl group. In IUPAC, in giving preference during allotting the locates. So your counting will start from this side. The ine gets the first carbon and the methyl group comes on the third carbon. So you call it 3-methyl-but-1-ine. Right? That is your compound. Now these are the 3 isomers that you will get for pentyne. And if we have to categorize these as position isomers and chain isomers, we know the first 2 are position isomers. In the first 2, the position of the triple bond is different. But this one has a different chain. So its relationship with both of these will be, if you relate this with this, the chain is different. So these 2 are chain isomers. Similarly, this one and this one, what is the relation between them? They are also chain isomers. These 2 are position isomers. In both of them, what is the difference? The position of the triple bond is different. But in first and third and second and third, there is a difference in the structure of the basic structure of the carbon chain. Therefore, these two will form chain isomers. Right? Let us now write down the isomers of hexane. So what will the formula of hexane be? C6H10, right? CnH2n minus 2. C6H12 minus 2 is 10. C6H10. Let us try and make the structures. So what are we first going to try? We are going to try and change the position of the triple bond and see how many structures can we get. Now, initially I'll just make the carbon skeletons because filling up of hydrogens can always be done. So let us make the carbon skeletons first and then we'll fill up the hydrogens. The first thing is that the first isomer could be that you have 1, 2, 3, 4, 5, 6 carbons. And there's a triple bond between the first carbon, right? That forms the first compound. So here there are 3 bonds already, so 1 hydrogen. This is forming 4 bonds, so it does not need hydrogen. 2 bonds, so 2 hydrogens, 2 bonds, 2 hydrogens, 2 bonds, 2 hydrogens, 1 bond, 3 hydrogens. Count the number of hydrogens, 3, 4, 5, 6, 7, 8, 9, 10. So you have C6H10, right? How would you name this? This would be hex 1 ine, right? The IUPAC name would be hex 1 ine. Let us now change the position of the triple bond to the second carbon. So you'll get 1, 2, triple bond is here, 3, 4, 5 and 6, right? The triple bond is between these two. Both the carbons are forming 4 bonds each. This will have 3 hydrogens. This has 4, no hydrogens, 2, so 2 hydrogens, 2 hydrogens, 1, 3 hydrogens. Count the hydrogens, 3, 4, 5, 6, 7, 8, 9, 10. Again it is C6H10. You have to confirm in the end that you always get the right formula. Now how would you name this? This would be this should be a capital. You're writing in IUPAC nomenclature, you start the name with a capital letter. Just as when you write your name, you start with a capital letter. So this would be hex 2 ine. The ine is on the second carbon. Now let us shift the ine to the third carbon. So 1, 2, 3, 4, 5 and 6. And between the third and fourth carbon, I have the triple bond. If I count from this side, 1, 2, 3, I again get the third carbon, which is different from these two, right? So which means that this would also be an isomer. You're not getting the same compound. This compound is different. So let us fill up the hydrogens. 3 hydrogens here, 2 hydrogens here, 4, 2 hydrogens here, and 3 hydrogens here. This would be hex 3 ine. Right? Hex 3 ine or hexane. Now, if I shift the triple bond between these two, I will get this structure. Only I'll be looking at it from the other side. Or if I shift it, let me see. If I shift it in this here, and let us ignore the hydrogens. If I shift it here, now I'll count from this side and I will get 2 hex 2 ine, which is nothing but the same compound. So I will not get any more position isomers. So what is the next thing that I can do? The next thing that I can do is start making branches. So when I start making branches, let me take this one first and make a branch in this. So you have CH, carbon, triple bond, carbon. I'm making just the carbon skeletons first. 1, 2, 3, 4 and 5. Let me make a carbon branch here. In another one, let us have the triple bond at the same place. And let me make a carbon branch on the other carbon here, right? And let me wipe this off too. Can I make any more carbon branches? Single carbon branches? I can't. Why? Because if I now try to shift the carbon branch to this carbon is already forming 4 bonds, therefore I can't make a carbon branch. So let us now fill up the hydrogens. This carbon is forming 3 bonds, so it needs only 1 hydrogen. This is forming 4 bonds, no hydrogen, 2 bonds, 2 hydrogens, 3 bonds, 1 hydrogen, 1 bond, 3 hydrogens, 1 bond, 3 hydrogens. Right? 1 bond, 3 hydrogens, 3 bonds, 1 hydrogen, 4 bonds, 3 bonds, 1 hydrogen, 2 bonds, 2 hydrogens, 1 bond, 3 hydrogens. Let us count the hydrogens. Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Correct. 3, 4, 5, 6, 7, 8, 9, 10. They are all correct. Let us name these now. This now it will become pentyne. So again, the methyl group will not get importance, the ion will get. So we'll give the lower locant to the ion. So we'll start counting from this side. 1, 2, 3, 4. So this would be 4 methyl pent 1 ion. Right? This is 4 methyl pent 1 ion, and this would be 3 methyl pent 1 ion. Right? What have we done? We have given the lower locant to the ion, and the methyl group is that gets the higher locant. But since you, in writing the nomenclature, you have to write the substituent first. So you write the locant, write down the substituent, parent hydrocarbon, and then write the locant and the whether it is an ane, or ion. So it is pent 1 ion, 3 methyl pent 1 ion. Now tell me, can we have made single branches. If I wanted, I could now shift this, use this one and make branches, make a single branch. So instead of 1 ion, let us have 2 ion. Let the double bond be between the second and the third carbon atoms, and let us make branches. 1, 2, the triple bond is between the second and third carbon atom, 4, 5, and there has to be a branch. Right? So now fill up. 3, this already forms 4 bonds, this also forms 4 bonds, this forms 3, so this is 1, 3 and 3. So 3, 3, 3 is 9 plus 1, 10. So C6, H10 you are getting. And what will be the name of this isomer now? The ion or the triple bond is between the second and the third carbon atom, it gets the lower locant, and the methyl group is present on the fourth carbon. So we'll write this is, yeah, so this is 1, 2, 3, 4. 4 methyl pent 2 ion, right? It is 4 methyl pent 2 ion. Now, is it possible for me to make a single branch anywhere else? Both these carbons are already forming 4 bonds each. You cannot form a branch with them. This is a terminal group. A terminal group, you cannot make a branch on the last carbons. So your only possibility was to make a branch on this carbon. So with the triple bond between second and third carbon, there is a possibility of only 1 branch. Now, is there a possibility for you to make 2 branches? Let us see. To make 2 branches, we have noticed that in this structure, only 1 branch is possible. So we will have to go back to this structure and see if we can have 2 branches. So we'll write 1, the 6 carbons will be 1, 1, a triple bond between 2 carbon atoms, 2, 3, 4, 5 and 6. I got 6 carbons. There's a triple bond here, so this will be H, already 4 bonds. This is already forming 4 bonds, so this will be CH3, CH3, CH3. So 3, 6, 9 plus 1, 10, and you again get C6H10. Now, what will be the name of this compound? The ion is between the first and the second carbon. So it will be, now the parent hydrocarbon has only 4 carbons. So it is butyne. And it has 2 methyl groups, these 2. So you write, and both of them are on the 1, 2, 3, third carbon. So we'll write 3, 3 dimethyl, right? 3, 3 dimethyl but 1 ion, hash ion. Right? Is it now possible to shift the triple bond anywhere else? Of course not. Why? Because this carbon is already forming 4 bonds. so is this carbon. So there is no possibility of shifting this triple bond anywhere else, because the only possibility would have been here or here. If I would have shifted it here, I would have had to shift the two branches on this carbon. It would be the same compound looking from the other direction. So this is the only structure that is possible. So how many isomers did we get in the case of hexane? 1, 2, 3, 4, 5, 6, 7. There are 7 possible isomeric forms. Now, what you have to do is see which ones are position isomers and which ones are chain isomers. And you have to relate them, the pairs. This, this, this. These 3 are position isomers, right? These 2 are also position isomers. How? Although the triple bond is at the same position, here their position is different in the case of the methyl group. Here the methyl group is on the 4th carbon and here the methyl group is on the 3rd carbon. So these 2 also have a relation between each other, and that is, you would say, a position isomerism, because the position of the methyl group is different. But if I relate this with this or any of these 2, that would be chain isomerism, because here it's a straight chain, here it's a branch chain. If you relate this with this, again, it is a position isomer. Why? Because the position of the triple bond is different. The methyl group is the same. If you relate this with this, it is, again, the position of the methyl group is also different and the position of the triple bond is also different. So you can draw such relationships between different pairs and see whether they are position isomers or are they chain isomers. Here there is a single branch, here there are 2 branches, all these have single branches. So if you relate them with each other, you will say that here or if you relate any of them with the straight chain ones, you will call them chain isomers. So this was nomenclature and isomerism in alkynes. And with this, I'll wind up today's video. If you want to watch other videos of this chapter, please click the link that is going to appear on top of your video. And well, if you found my video helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching. Bye-bye for now.